Hi there. In this video, we will analyze some more problems using the radian measure. Let's start by drawing the unit circle. Circle with radius 1 and some angles to give us a guideline. Since we want values for theta being negative 7 pi over 4, we go clockwise when labeling our angles. Now let's label the angles dividing by 4. Again, going clockwise for negative angles. And now we arrive at negative 7 pi over 4, which is in the quadrant 1, so we can use the reference angle of pi over 4, which is the same as 45 degrees. Now let's label how to get the ratios for each trig function. Might as well label the key sides of our triangle we have in the circle now. This comes from common values of trig functions. Now that we have labeled everything, we can figure out the ratios. Secant negative 7 pi over 4 is hypotenuse over adjacent, so 1 over root 2 over 2. Cosecant negative 7 pi over 4 is hypotenuse over opposite, so 1 over root 2 over 2. Tangent negative 7 pi over 4 is opposite over adjacent, so 1. Cotangent negative 7 pi over 4 is adjacent over opposite, so 1 as well. Next example. Here we are given a ratio and we want to find some others given our information. Let's label a few things and draw a diagram. Cosine is adjacent over hypotenuse, and pi over 2 is 90 degrees. Now let's find the opposite side using the Pythagorean theorem. Now that we have all the values we need, we can find the corresponding trig values. Sine theta is opposite over hypotenuse, tangent theta is opposite over adjacent, and secant theta is hypotenuse over adjacent. So our ratios are sine theta is 4 over 5, tangent theta is 4 over 3, and secant theta is 5 over 3. Another example. We want to find the 6 trigonometric functions given the following information. It may help to draw a diagram. Let's plot the point and label all the quadrants. Draw a line and the angle beta. Now that we can see the right triangle in our diagram, we can label some key components like x, adjacent side, y, opposite side, and r, hypotenuse. Now let's label how to find each of the trigonometric functions. figure these out, we do need to solve for r. So let's do that using the Pythagorean theorem. Solving, we get r is root 84, or 2 times root 21 if you simplify. Either answer is good. Now we can find all the ratios. And done. Now let's look at the graph of sine and cosine functions. To make this simpler, we can use the unit circle on the left to help with x and y values. Our x values are the angles on the unit circle, and y values are the y values on the unit circle. Since the unit circle has highest or lowest values of plus or minus 1, we know y values will never go above or below that. To plot some points, we start at x equals 0. And on the unit circle, we see y is 0. So plot that. Going counterclockwise on the unit circle, we look at x is pi over 2, and the y value on the unit circle is 1, so plot that. Then we move to x equals pi. The y value on the unit circle is 0, so plot that. Then x equals 3 pi over 2. We get negative 1 as the y value, which we can see on the unit circle, and back around to 2 pi, y is 0. Now we just connect the dots, and there we have it, the sine function. Looks like a wave. A small note, I chose the y values I did for x because those are fairly easy values to spot on the unit circle. I could have used other values like x is pi over 3, but its y value isn't as nice as 0, 1 or negative 1. For negative values, remember on the unit circle, angles go clockwise. We can do a similar process plotting those points. Look at negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi, and connecting the dots to complete our picture. Another note, notice from negative 2 pi to 0 and 0 to 2 pi, the graph is the same. This is referred to as the period of the graph. In this case, since from 0 to 2 pi has all the values of the function, then the graph just essentially repeats itself. So we say that the period of this function is 2 pi. Just to make note of things, the period of the graph is 2 pi, since that contains the whole shape of the graph. Also, we saw that the graph never went above or below -1. This is known as the amplitude of the graph. Another thing to possibly notice is that the x-axis basically cuts the graph in half, right? This is known as the midline. In this case, y is 0. We graph the cosine function in a similar way. We plug in x values that relate to angles on the unit circle, and the y values correspond to the x values on the unit circle, since cosine theta equals x over r. Also, positive angles on the unit circle, we go counterclockwise, and for negative angles, we go clockwise on the unit circle. At x equals 0, or the angle 0 on the unit circle, our y is 1, since x is 1 on the unit circle. At pi over 2, the unit circle gives an x value of 0, so it's 0 on the graph as well. When the angle is pi on the unit circle, x is -1, so on our graph, y is -1. At 3 pi over 2 on the unit circle, x is 0, so y is 0 on our graph. And at 2 pi on the unit circle, x is 1, so on our graph, y is 1. Now we just connect the dots, and voila! We have what cosine looks like. We will continue with negative values as well, though. At -pi over 2, x is 0 on the unit circle. On our graph, y is 0. At -pi, x is -1 on the unit circle, so y is -1 on our graph. At -3 pi over 2, x is 0 on the unit circle, so y is 0 on our graph. And at -2 pi, x is 1 on the unit circle, so y is 1 on our graph. And we connect the dots and we get a fuller picture of cosine. Since from 0 to 2 pi gives basically the whole graph, after that it just repeats. The period is 2 pi. Amplitude is 1 since it doesn't go above 1 or below -1. And the midline that essentially divides the top and bottom of the graph is the x-axis, or y equals 0. A note when graphing these two functions. You get an idea of the whole graph plugging in values between 0 and 2 pi. So it's a good idea to always start with that interval when thinking about what x values to plug in. And remember that easy values of trig functions are at places like 0, pi over 2, pi, 3 pi over 2, and pi. If you can remember that, it may be easier to graph functions that look the same, but aren't exactly the same, like this example. First, notice that this is just cosine function with stuff added to it. For example, instead of cosine x, it's cosine x over 2. Also, there's a +1 at the end of the function, where the original function of cosine we graphed didn't have that. So that means instead of the midline being at y equals 0, it will be at y equals 1. So let's draw that. Also, you may remember that cosine had amplitude of 1, and this is a similar graph. So our graph will never go above plus or minus 1 from the midline. So let's mark that too. Now we want to plug in some key values. And remember, some easy values were for angles like 0, pi over 2, pi, 3 pi over 2, and 2 pi. Also, we know from previous graphs that if we plug in values from 0 to 2 pi, we basically get the whole graph. So let's start with that. Just remember that instead of x, we have x over 2. So we'll have x over 2 to be between 0 and 2 pi. Now let's manipulate this inequality to have x in the middle by multiplying everything by 2. What's nice about this is that now we have an interval of x values that we can plug in to get the whole graph. On top of that, that gives us the period of the graph too, 4 pi. Now we just need to figure out some nice, easy values to plug in. A couple of fairly easy points right off the bat could be the ends of our interval, 0 and 4 pi. So let's do that. Plugging in those two values for x, we get out 2 for y. So let's plot those and label our x values from 0 to 4 pi, since that is our period. This is where it can get a bit confusing, but hopefully not. Haha. Now we need some more values to plug in. Remember, we like values that are easy, and there are 5 points that are fairly easy. 0, pi over 2, 3 pi over 2, and 2 pi. We actually did the first and last points, except 2 pi was really 4 pi since the x was cut in half. So we need to figure out the easy values for pi over 2 pi and 3 pi over 2. So we simply set them each equal to x over 2 and solve for x. For x over 2 equal to pi over 2, when we solve for x, we get x equals pi. So we plug that in and plot the point on the graph. For x over 2 equal to pi, solving for x, we get x equals 2 pi, so we plot that on our graph. And for x over 2 equals to 3 pi over 2, solving for x, we get x equals 3 pi. And we plot that. Now we just evaluate and plot the points. Whoops, I was plotting points and didn't even realize you couldn't see that. Sorry. And yay! We can connect the dots and see what our graph looks like. Still looks like cosine, right? Just moved up and stretched horizontally. Since we know we have the whole graph, it just repeats itself. We can extend the graph on the left side as well if we want. Just to give a better idea, here's the graph of cosine and our graph, which was the same but a little different. Notice that really our graph is stretched out horizontally, which was a result of the x over 2 part of the function. And also, our graph was moved up by 1 specifically, and that was the result of the plus 1 at the end of our graph. Here's a zoomed out version of the two graphs.